Phil, back for some more MCAT podcast. How are you today?
Good. It's a bright, sunshiny day. Birds are singing. Summer is here. Okay, it's not officially summer, but it feels like summer.
It feels like summer. Yes, even though we can't go outside to actually feel it, we can see it through the window.
Right. I can see the birds.
Yes. All right. So we're continuing our journey down Blueprint MCAT full-length 1, which if you sign up for the diagnostics exam, you get the full-length 1 for free. And so take that and then come back and listen to these and watch the videos and walk through the exam with us. And hopefully you can figure out how to get that 528. That's the plan.
Yeah, we get to do a little bit of nuclear physics today, which is everyone's favorite thing to just do on a...
It's my hobby, actually.
Yeah.
No. All right, so let's go ahead and walk through. If you're listening to this, you can watch on the YouTube channel. If you're watching on the YouTube channel, you can take us to go on the podcast. So lots of options for you. So go ahead and take a dive into this passage.
Yeah, so we'll go ahead and take a look at this very first bit here. It's questions 6 through 9 on the exam. So we're going to have, 4 questions. So nuclear power plants harness the energy of uranium-235 fission and convert it to electricity. Fission is initiated by bombarding uranium-235 with neutrons, which splits them into smaller atoms, which then induce fission of nearby uranium-235, causing a chain reaction that releases energy. Now, obviously, kind of like hopping in here, this is very high level physics, nuclear physics sort of thing. But the MCAT does test stuff with this, like the different kinds of decays, fission versus fusion. What's just off the top of your head, Ryan? What's the difference between fission and fusion?
Splitting versus joining.
Yeah, there you go. You were thinking about fusion restaurants, weren't you?
No, yeah. Yes, Asian American fusion. Yeah.
Right. We'll have a Asian fission, and we just do the rice, nothing else on top of it. We're splitting it apart. So we're talking about fission here. So we're breaking this uranium into smaller units, which is going to release energy. So in 2011, power systems at Fukushima, Daiichi, NPP, and Japan were disabled by a tsunami, causing the release of radiation and volatile radionuclides, unstable isotopes that undergo decay, into the surrounding environment. In Fukushima, there was concern about the effects of the radiation and radionuclide contamination on human, animal, and plant life. Nuclear radiation can cause DNA, can damage DNA, induce cancer, and can cause cell death. Scientists investigated 2 examples of DNA damage believed to be caused by the accident, one in Japanese fir trees and one in humans. So obviously kind of like making this connection here to cancer, right? Like what's going on with like damaging DNA and mutations.
Yep.
Researchers noticed that the Japanese fir trees near the NPP had a higher rate of morphological defects than those in uncontaminated trees, including deletion of the leaders, shoots, and buds produced after the accident. And this is where you can kind of pause and just be glad that you don't need to know about botany for the MCAT. So what they're talking about here, you're probably not going to have any questions about. Yep. This led to concern about the release of radionuclide Iodine-131, an isotope with a half-life of 8 days that undergoes beta-minus decay followed by gamma emission. Because the body can concentrate iodine in the thyroid, exposure to these radioactive isotopes can cause thyroid cancer in humans. Now, this is the first sentence that I read, and I'm like, there's going to be questions here, right? We have this half-life stuff of 8 days. We got the beta minus decay, and gamma emission. The MCAT is going to expect you to know about the like alpha, beta, and gamma decay. And so you want to make sure that like you kind of have a good understanding of this. And there'll be some questions as we come across them. To assess the possibility that iodine-131 contamination was the cause of leader shoot deletions and thyroid cancer, researchers measured average 131 contamination levels in 5 areas, A through E, near the NPP, which is the power plant, each of which covered 6 square miles with similar populations. They measured the average number of leader shoot deletions of the 2012 buds and the incidence of pediatric thyroid cancer cases in the area between 2012 and 2014. The data is summarized below in Table 1. So we have this table here. What's your kind of like thought about just kind of like looking at this table overall?
So if you're listening to this again, we'll have the video up looking at it so you can check it out. But the table one, it's titled I-131 Contamination, Morphological Defects, and Thyroid Cancer. So they have 5 different areas here labeled from highest to minimal contamination of this 131 iodine, this liter shoot deletion rate per number of trees, which looking at this doesn't show any correlation that I could see with highest to minimal as far as the deletion rate per 100 trees. The cancer incidence, again, looks very similar. The cancer in 2012, cancer incidence in 2013 looks like there's a potential correlation from highest to minimal with almost double, more than double the cancer incidence a year out. And then the cancer incidence in 2014, so 2 more years, is 5 to 6 times higher. So obviously looking at this, the deletion rate doesn't look like there's a correlation potentially, but the cancer incidence obviously looks like, and I'm just guessing here, it looks like there's some statistical significance as time goes on.
Yeah, especially looking at the 2012 when they're all like pretty same within like 100 of each other. And then you look in 2014, we have 2,000 in the minimal contaminated area and 12,000 in the highly contaminated area. So something definitely going on there. Just side note, plants tend to not show mutations nearly as quickly as animals do because our cell division occurs at a higher rate. Once again, they're not going to test this on botany though. And so that might be why we kind of see this setup here.
Yeah. Okay.
So let's go ahead and look at the questions. So we got this first question. I'll let you kind of like tackle this first one.
Yeah. So question 6, which of the following are products of the decay of Iodine-131 or 131 iodine? Did you say 131 iodine? Is that how you say that? Or
Iodine-131.
Either way. All right. So A and B are both ionizing radiation. C and D are non-ionizing radiation. As far as I know, like to be cancerous and to cause effects, it has to be ionizing. So that's just I think a knowledge thing right off the bat. So I'm not even going to waste my time with C and D. I'm going to stay with A and B because we know that this 131 is causing cancer. And so we have, is that Xeon-131 and what's TE? Technetium or?
Tellurium.
Tellurium. So we have our periodic table. I could have opened up here and looked at TE. Of course, it doesn't give you the full name on that periodic table. That's all right. All right. Tellurium-131. So the question is Xeon or Tellurium-131. If I go to my periodic table and I look at iodine, so Xeon is 1 up, and Tellurium is 1 down, or 1 to the left, 1 to the right. So we have to go, okay, if I give up an electron, I'm assuming that's giving up an electron, a product of that decay. Where am I going on the periodic table? I think you go down to Tellurium, I think. So it'd be Tellurium-131, maybe. Yes.
So the passage tells us that we have a couple kinds of radiation occurring. We have gamma emissions, so we're emitting, like we're doing gamma decay, and we're also doing beta minus decay. So gamma decay, it's like that's my favorite kind of decay, which I don't know, that might put me in like a weird thing to have a favorite kind of decay. But gamma decay, just the nucleus reorganizes slightly and it becomes more stable. Right. And so it goes from high energy to low energy. So it just emits energy because we can't create or destroy energy. So if it goes from high to low, it's got to give off that energy somehow, and it gives it off as light. So it just emits a photon. It's the highest energy photon that exists in terms of types. So it's not like a radio wave or visible light. It's going to be a gamma ray, which is why it's called gamma decay. And that's got enough energy to knock an electron off of all sorts of molecules, which is why it's damaging to DNA. And so you're absolutely right with the ionizing radiation. I mean, that's why it's dangerous, because it's ionizing our DNA and making it reactive by knocking an electron off of it. The beta decay is a little bit trickier because there's 2 types of beta decay. There's beta plus and beta minus. And so in one case, a proton turns into a neutron. And in one case, a neutron turns into a proton. So depending on the kind of decay we have, like we're going to either gain a proton or lose a proton, which is where the tellurium and xenon come in. And we got to figure out which directions it's going to go. The easiest thing for me is I always tell the beta decays, because I know that the reaction has to be balanced. And so if I have a proton turn into a neutron, that means I go from a positive thing to something with no charge. So then the decay product I get must be positively charged. So that's going to be beta plus decay, which would be a positron. So you have a proton turns into a neutron and a positron. Or beta minus, that's a neutron turning into a proton and an electron. And that way it's balanced in terms of charge there as well. So because we know we're getting an electron, because the answer has got to be A or B because it's ionizing, and that means we must have a neutron turning into a proton because we're also getting this negative charge as well with the electron. So that means we're gaining a proton, so the iodine is going to turn into xenon. If it was beta negative decay or beta plus decay, then it would be turning into tellurium. So you need to be able to pull those apart. The easiest way is to just make sure that it's a balanced reaction.
Okay. So if one of these answer choices, kind of ignoring the passage, if one of these answer choices was ionizing radiation and a what, that would make it tellurium for this answer?
So you would have to get a positron from that, because then you'd go from a proton to a neutron and a positron. That way it's positive on the reactants and products side. But like we also need ionizing radiation because it says it's doing gamma decay. But yeah, other than that, like the tellurium and positron that we see in answer choice D, that fits perfectly with beta plus decay. But we also need the gamma decay as well.
All right, that's question 6. Question 7.
So why did the researchers choose to study pediatric rather than adult thyroid cancer cases? So this is going from like the hardcore physics to the, kind of hardcore biology side of things. So thyroid cancer is not otherwise present in children. It's answer choice A. Thyroid cancer is not otherwise present in adults. Answer choice B. Children receive a higher relative dose of iodine-131 at the same contamination levels, which is C. And then D is children receive a lower relative dose of iodine-131 at the same contamination level. Yeah,
so I think, and it's funny, just on the recording here, I had already selected C. I think I was playing with this test earlier, but I think I was just randomly clicking things, but I think it's the right answer. So they study children because the children's thyroid is taking up more iodine because the children are active and their what do you call that level is really high, and so they're taking up a lot more versus their metabolic level is higher versus adults, where the metabolic level is a little bit lower. We have a little bit less concern of that uptake.
Yeah. Plus, this, the idea that just children are, generally speaking, smaller than adults. And so, if a child takes in like 5 radioactive iodines and an adult does, like that's a higher concentration in the kid because it's just a smaller person. Yeah. Any thoughts on A and B? You're right. It is C for this one. So the children have a higher dose at the same contamination levels. But A and B are kind of interesting.
Yeah. So thyroid cancer for A is not otherwise present in children. I don't know what the incidence of thyroid cancer in children is, so I wouldn't comment on that. Thyroid cancer is not otherwise present in adults. Obviously, that's not true because we have lots of thyroid cancer in adults.
Right.
So
just having some exposure, like those are really bold things. Like, oh, these thyroid cancers just don't happen. Like, obviously,
those are the extremes.
Thyroid cancers, yeah. Right? And even from the table, they show us that the incidence rates of thyroid cancer in like the minimal area was 2,000 in 2012, which is when the nuclear power plant, I want to say exploded. Didn't explode.
It didn't explode.
Yeah. Started leaking. That's a better way to put it.
Okay. Yeah, and I think if we actually look at the passage kind of tells us that A is not right because they tested the incidence of pediatric thyroid cancers, and there was pediatric thyroid cancer, so A can't be right because the passage tells us there are cancers in the pediatric population. Or it says not otherwise present. So maybe if there wasn't a radioactive leak, then maybe, I don't, that's too extreme.
Yeah.
Okay. So question 8, several families in areas 4 and 5 who read the results of the study believe that their children have no increased risk of developing thyroid cancer. Is this conclusion accurate? So again, going back to areas 4 and 5, we have the low and minimal exposure, that contamination of the iodine-131. The cancer incidence in 2012 was 2,377 for low, 2,344 for 2014. So over 2 years, the incidence did not increase. In minimal, there was 2,200 in the minimal area and still 2,200 in the 2014 sampling. So it looks like there's no increase at all. The incidence is the same across the board. And so reading the answer choices here, A, no, the mutations caused by iodine-131 exposure may take more than 3 years to manifest as cancer. B, no, iodine-131 has a half-life of only 8 days. C, yes, Table 1 shows that there was no increase in cancer in areas 4 and 5 in years 2013 and 2014. And D, yes, the radiation given off by iodine-131 is not mutagenic. So automatically D, right off the bat, we know that that's not true, right? So the question is the conclusion, right? Just making sure that we're answering the right question. The question is the conclusion that these children have no increased risk true? And so I think the easy thing to jump to is just to say yes, right? It must be true because the table says from 2012 to 2014 there's no increased risk. But I think that's too easy to jump at. And what if we tested in 2015 and now all of a sudden there's a huge spike in these cancers and it just took longer to manifest? And so I would probably say the answer here is A, no, the mutations caused by iodine-131 exposure may take more than 3 years to manifest.
Yeah, this is why it's tricky, because if you go just purely from the data on the table, the C is the right answer, but that's not the correct choice to this question. The correct choice is, this may take years to show up as cancer. That's how this question is actually testing some outside knowledge of knowing that like being exposed to something makes you more likely to get cancer later, and that may not show up immediately. That may show up way down the line. Like if I was a heavy smoker in my 20s and 30s, I might be at higher risk for lung cancer, even in my 60s, even though I haven't smoked for 20 years.
Yeah. Would you say that it requires outside knowledge, or what the MCAT is critical thinking to go, well, wait a minute, right? It's just like, it's after 2 years, it's not like, okay, there's no risk, I'm scot-free. Like, it's just critical thinking to go, does that really make sense?
Yeah, there's kind of a combo, this like scientific reasoning of like not extrapolating too far, right? Like if I bought a wind chime and then my house didn't blow down in a tornado, that doesn't mean the wind chime stopped the tornadoes from blowing my house down, right? Like there's some conclusions you can't make because you just don't have enough data. Yeah.
You smoke one cigarette at 14 years old and you get lung cancer at 83. Oh, it finally showed up.
Yeah, that was the one.
Yeah. Yeah. Okay.
And so, so a little bit of that, a little bit also, the MCAT definitely wants you to kind of understand what's going on with cancer biology. Cancer shows up on pretty much every exam. I've never seen an exam that didn't talk about cancer, at least somewhat. Okay. And so just this idea that the mutations that happen, like I may mutate my DNA and not get cancer immediately, right? Like you can have, it takes an accumulation of lots of mutations in order to lead to cancer. And so,
that's what P53 is for, right?
Right, exactly.
Nerd stuff. All right. Question 9. This is you.
So it's found that small to moderate doses of iodine-131 are more likely to cause thyroid cancer than extremely large doses. So this seems a little counterintuitive, right? Yep. Which of the following provides the best explanation for this observation? So A says that small doses are not absorbed by the body. B is that extremely large doses of iodine-131 are not absorbed by the body. C says the amount of radiation released by large doses of iodine-131 is enough to damage DNA without killing cells. And D says the amount of radiation released by small doses of iodine-131 is enough to damage DNA without killing cells.
Interesting. So A just doesn't make sense because it just told us that small doses are more likely to cause cancer, so they have to be absorbed. So A is immediately gone. And I was just playing as you were talking. I'm like, is there a way to cross off answer choices? But it doesn't look like there is.
There is. That's part of that early training thing that happens at the beginning.
There we go. If I highlight it and then click the strike through.
Right, exactly.
Okay. All right.
There's also keyboard shortcuts. I don't use the keyboard shortcuts that much during the exam, except for highlighting. I find it really useful for highlighting, but there is one for strike through. I'm not sure what the keyboard shortcut is, though.
That's all right. All right. So I struck through, if that's a past tense, of answer choice A. Extremely large doses of iodine-131 are not absorbed by the body. So that would potentially answer the question. The question that I have is that true? So I'll leave that one potentially. C, the amount of radiation released by larger doses of iodine-131 is enough to damage DNA without killing cells. That just doesn't make sense based on like what cancer is. Like cancer is damage to the DNA. Obviously, the cells have to live to transfer that DNA down its lineage. So just from a biology standpoint, that doesn't really make sense. Physiology standpoint. D, the amount of radiation released by small doses of iodine-131 is enough to damage DNA without killing cells. So that one is interesting. So it's the opposite, right? Of smaller doses. So then that would, in my mind, it makes me go, oh, maybe the large dose does kill the cells, which is why it doesn't cause cancer. Because all of the DNA that it does damage just kills the cells to begin with, and maybe it just kills the person, and so you don't have cancer, you just have a dead body, or the cells are just dead and it can't cause enough. So, yeah. So I'm left with B and D. B just seems weird, right? The body's going to absorb what the body's going to absorb. I don't know why it wouldn't absorb large doses. It's like, oh, that's too much iodine. That's too much radioactive iodine there. I don't want you right now. So B just doesn't make sense logically, and so I'm going to go with D.
Yeah, exactly. That like the idea that it does absorb. If you put like 5 iodines, your body will pick up the 5, but if you put 50, it won't pick any of them. Yeah. Right. Like that seems a little bit weird. Maybe like there's some weird flow through that it'll only pick up 5 and the other 45 just can't be handled.
But it still picks it up.
But it would still pick it up and you would still get cancer and like that would be the same. So the idea here is you're absolutely right. So D, just the high doses of iodine-131 basically just takes a bazooka to the DNA, which means it's not going to turn into cancer because the cell is just dead. Yeah. And so the small mutations without killing the cell is what you kind of need in order to develop cancer here. So kind of an interesting scenario where the middle ground is actually the most dangerous. Yep. Lots of iodine. Kills the cells. No iodine, you're fine. Okay. Middle cancer.
Yeah, and maybe that's what we see potentially, right, in the real world, is you have lots of deaths very early on. It's not from cancer; it's just from all of the cells dying from what's going on. Very interesting. Okay, so that's the end of this passage, so we'll stop here. But for those of you still listening, there's a little Easter egg. Go and watch the video and tell me what is wrong with Phil's stethoscope on his skull. Phil, what's wrong with your stethoscope on your skull?
Are you talking about Olaf?
Olaf, yeah, sure. If that's what you want to call your skull. Does it have a mustache?
He does.
That is funny.
That's from a Cinco de Mayo party when Olaf just decided he liked it, so he's wearing that.
All right, great.
So the big problem, other than a dead body would probably not need a stethoscope. Is the stethoscope is not in the ears.
Yeah, it is not.
No, it's just in the jaw. It turns out the ear holes doesn't stick very well in there. So just
awesome. The zygomatic arch is not where we listen to things. So
maybe there's some bone conductive. Maybe you could. I've developed a new kind of
bone conduction. Yeah. They do have bone conduction headphones. I haven't tried them, but supposedly they're good. And then it's interesting, just a random tangent. I have a friend whose daughter is a nurse who is deaf, became deaf at 3 from bacterial meningitis and has a cochlear implant. And so she uses a special stethoscope that has a Bluetooth attachment to her cochlear implant.
So she doesn't even have
really
to, she's not corded to the stethoscope.
Nope.
So she could have the nurse hold the stethoscope up to patients in other rooms.
Yeah.
And she's just like sitting in her office listening to heartbeats.
Well, she is a nurse herself, so.
Right.
But yeah, she could have the nurse students be like,
right.
go put the bell on patient 3. So, all right, fun thing there with the what do you call that? The skull. Olaf, yeah. As a thing. All right. Thank you, Phil, for that wonderful walkthrough of radiation.